Good afternoon, everyone, and welcome to today's webinar, Cast Iron Analysis Using Advanced OES Technology. I'm Shannon Wetzel, Managing Editor of Modern Casting Magazine, and I'll be introducing you to today's speaker and helping out with Q&A at the end of the session. The webinar will be recorded and made available to today's attendees. You will receive an email with a link to the recording within a week after the webinar. The presenter, Mike De Leon, will be answering questions at the end of the session. You can type your questions in at any time during the webinar in the question box in your webinar control panel. Now let me introduce our speaker, Mike De Leon. Mike has been with Spectro and Analytical Instruments for 15 years, starting in the XRF Applications Group. Now he's the USA Metals Analysis Sales Manager and the Applications Department Manager. He works closely with field sales and marketing to ensure the right analytical solution is provided for Spectro's customers. He also coordinates projects for Spectro Analytical Instruments USA demonstration labs, providing customers with feasibility studies and demonstrations for all of Spectro's product lines. Mike is also a very active member in various ASTM committees. Now let's hear from Michael.
Thank you, and welcome to our webinar today. My name is Michael De Leon, and I am the U.S. Metals Analysis Sales Manager at Spectro Analytical Instruments. Today, I would like to present an opportunity for the determination of carbon and cast iron using a spark spectrometer. I would like to start with some general information about carbon and cast iron and why carbon analysis is important, continuing with sample taking procedures and the related effects. After that, I would like to discuss the analytical challenge we face when using a spark OES and how we solve that, followed by some practical examples and some analysis results with the conclusions and benefits. Cast iron can roughly be separated into two groups, either white cast iron or gray cast iron. The most common cast iron is gray cast iron. It mainly has around 2.5 to 4% of carbon and 1 to 3% of silicon, the remainder of course being iron. Due to the graphitic microstructure, the fractures of the material have a gray appearance. Therefore, it's called gray cast iron. Its metal structure evolves due to a slower cooling process. Now, the other type, the white cast iron, has a white fractured surface as you can see up here. This is caused by the presence of an iron carbide precipitate. This is called cementite. It has a lower silicon content than gray cast iron, and due to a faster cooling rate, the carbon in the white cast iron precipitates out of the melt as a metastable phase cementite. The structure of a cast iron can either be white or gray, and this depends on the solidification process. So a white cast structure can efficiently be analyzed with the SpectroMax and SpectroLab, our stationary analyzers, especially the carbon content. It can also be analyzed by our mobile spectrometers, the SpectroTest and SpectroPort, but with the limitation that the carbon content might not be precise enough to monitor a melting process. As the gray cast structure evolves due to a slow cooling rate, the carbon distribution in the metal is not homogeneous. Analyzing the carbon content in such a gray cast iron is nearly impossible, neither for a mobile nor a traditional stationary optical emission spectrometer. So, sample molds are a critical part of this step. We need to consider for sampling. There are various sizes and shapes available on the market. Both pictures you see here show a solid copper block mold, which are specifically made for cast iron sampling. The copper block works like a big heat sink to chill the molten metal as fast as possible. There are also molds on the market which are using water cooling. The selection always depends on you, the customer, your requirements. After a sample has been taken, the mold needs to be cooled down to a certain temperature, otherwise the next sample will be chilled too slowly. Depending on the frequency of sampling, 2 or more of these sample molds may be required. So a little more on the sample taking. During the sampling, the operator needs to be very careful not to introduce slag into the sample. When using a cold copper mold, operators can prevent cast skins from previous samples. This is another reason why it is advantageous to have more than one mold, or at least the mold needs to be cleaned with a brush in between samplings. At least there, the volume of the mold and the thickness of the sample have to match. Our initial impression is that sample preparation may seem to be the most routine aspect of an analytical protocol. However, it is so critical that analysts realize and remember that a measurement is only as good as the sample preparation that preceded it. If an aliquot taken for analysis does not represent the original sample accurately, the results of this analysis are questionable. As a general rule, the error in sampling and the sample preparation portion of an analytical procedure is considerably higher than that of the methodology used for the analysis. Sample preparation is so essential for the measurement process and to achieve reliable results. For measurements with the spectral test or spectral port in the field, you can use a hand disc grinder, or if available and possible, a stationary disc grinder like the one on the right can be used as well. For analyses with the SpectroMax or SpectroLab, it's preferable to use a stone grinder or a stationary disc grinder. White cast iron can be analyzed sufficiently with the spectral test and spectral port, our mobile spectrometers, but as mentioned before, the carbon content might not be precise enough to control a melting process. Examples will follow shortly. A higher chromium content of around 1% in the cast iron does have an influence on the metal structure, however. This allows analysis similar to what is possible with white cast iron. Again, example measurements for such material will be in the slide after next. For gray cast iron, you will need to spark the same spot a few times without moving the probe. At that point, a remelt process starts. You can get an approximate analysis after 2 or 3 burns. This way, it is possible to control the alloying elements, except for the carbon, with a mobile spectrometer. Measurement results of a gray cast iron sample will be shown on the second slide after next. Here you can see the results from 2 certified reference materials which represent white cast iron performed on a mobile instrument. You can see the excellent precision of analysis of the alloying elements, and the carbon's not too bad, but it's not precise enough for our needs to control. This slide shows comparison measurement results between a white cast iron and a gray cast iron performed on a mobile instrument. Both samples do have the same chemical composition. The analyses are quite precise except that of carbon. Finally, measurements of 3 different spots. So what we did here was take the probe from our mobile spectrometer, hit it 4 or 5 times on the same spot without moving. And we did that 3 different times. You can see here the initial burn on the spots of the gray iron show a very high carbon content. Then we start to get a remelt effect with the soluble carbon content being analyzed in subsequent burns. And this way you can get an idea of the carbon content for some applications. Note again that the alloying elements results are extremely precise. So that's for mobile spectrometers, which have come a long way, but with stationary benchtop or floor standing, we have additional capabilities. White iron analyzed by the SpectroMax and SpectroLab have very precise analyses, including carbon gray iron. However, carbon gray iron still has the same problem that insoluble carbon is discharged in the first burn or 2 on the same spot, but you can still control the alloying elements. We have, however, a special analytical procedure to do better than that and obtain consistent carbon content when the free carbon content is less than 6%. We call this the Iron 25 program, and it uses a different algorithm than our standard cast iron method. This method measures the carbon during the pre-burn time and combines some data with the analytical burns in order to determine the total carbon and not just the carbon in the solution. So let's get into more detail. Again, as you know, carbon is the most important element in cast iron. It therefore has to be monitored constantly during the melting process. It is so crucial for the chemical composition of the melt. Sample taking, as I mentioned before, is extremely critical. Chilling too slow produces graphitic inclusions, free graphite. However, it is well known that traditional spark OES systems need completely graphite-free samples to produce accurate results. Completely graphite-free samples are also known as the white samples in white iron. In real life, it takes a lot of experience and perfect sample taking to produce this so-called white cast iron structure on a regular basis. In other words, it's very difficult. And we have to accept partly gray samples. This is the reason why we developed our new Iron 25 program. So let's start analyzing this a little bit further. Starting with laminar cast iron, these samples are typically partial gray. Analyzing these samples, the carbon determination is always too high. For this kind of cast iron, an extension of the pre-burn time to around 60 seconds can solve this problem. Another workaround would be to analyze a few times on the same spark spot without moving the sample until the carbon value gets stable. Laminar cast iron represents approximately 60% of the total cast iron production. If the sample contains free graphite, it is possible in most cases to remelt the analysis area into a white iron type structure. The sample stays in one position on the spark stand. The concentration levels of carbon drops from a very high value, about 6%, after each pre-burn cycle, while the differences decreases until it stabilizes. 2 or 3 results with good repeatability show the correct carbon result. Switching to globular cast iron, we do see a different picture. Analyzing partial gray samples of this material, we typically see that carbon is determined too low, as opposed to with the laminar where it was too high. On the other hand, we would chill the samples extremely slowly. If we were to chill the samples extremely slowly, it would result in big graphite inclusions and might lead to super elevated carbon values. So that's not the solution to determining the correct carbon values for this kind of cast iron. Globular cast iron covers around 30% of the total cast iron production. 45 to 50% is required by the automobile industry with extremely high quality requirements. 20% of that would be used for special containments with thick walls, and 30% covers the tube industry. The carbon results are needed for great process control. So, let's take a look at the analytical problem we are facing with globular cast iron. On the right side, you can see a structure analysis result of such samples. Clearly, the graphite inclusions can be determined. The evaluation of the structure analysis is saying that the analyzed sample has a class 6 free graphite size. In the table on the left, we can see that for the class 6 size, we have an inclusion size from about 30 to 60 microns. When analyzing such a sample on a traditional Spark OES, the carbon results are measured too low at 307 compared to 363% as the true value coming from a combustion analyzer. The difference is too large to effectively run a process control using a traditional Spark OES instrument with a traditional method. Looking at another example, on the left side is our class 6 size sample with 3.63% true carbon instead of 3.07% analyzed. On the right side, we do have a structural analysis of a class 7 sample. Looking at our table again, we can see that the size class 7 has an inclusion size from 15 to 30 microns, so they're smaller than class 6. Back to the comparison of the two reports, the different sizes of inclusions can clearly be determined. Analyzing the class 7 size sample on a traditional Spark OES, we measure 3.46% carbon, whereas the combustion analyzer measures 3.65%. According to these results, we can guess that there is a correlation between the size classes of the free graphite and the differential between combustion and Spark OES. Larger inclusions are leading to larger deviations in carbon concentration. On the other hand, smaller inclusions are causing smaller deviations. On the next slide, we would like to take a look on the intensities of the sparks during the pre-burn phase. Every dot represents a packet of about 10 sparks. The left chart represents a white iron sample, which means no free graphite inclusions. On the right, we have samples containing about 0.5% free graphite. On both charts, the carbon signal is shown on the top, and the signal of the iron reference line is underneath. The carbon signal for the white sample is quite stable after the stabilization phase of about 150 spark packets. For the sample containing free graphite, however, you can see a different picture of the carbon intensities. After a short stabilization phase, we see high carbon activity of approximately 150 to 200 spark packets, starting with higher intensities than in the first example. So with this information, maybe we can determine the free graphite with the Spark OES. Just to give you a little bit more background about Spark OES, let me bring back this cool image from earlier. This shows what's happening during the pre-burn phase on the surface of a sample. The picture shows a micrograph of a pre-burn on a cast iron sample. Around the burn, you can see the globular graphite inclusions, but in the area close to the spark craters, the graphite inclusions are gone. They are burned out, and this behavior is leading to determination of lower carbon content compared to the combustion analyzer. So now I would like to show you a short video how an analyzer would analyze cast iron on one of our Spark OES instruments. We are about to analyze a partially gray globular cast iron sample. Looking again at the pre-burn spot, we can see the free graphites in the area of the pre-burn spot are evaporated and no longer present. As you see in the initial pre-spark, we see spiky carbon activity, and due to the fact that the free carbon is evaporating during the pre-spark, it is not possible to determine an accurate carbon value using conventional Spark OES. In summary, traditionally, it is not possible to make any conclusion about the sample quality, and incorrect carbon values may be presented without any warning. And here comes the solution, which we are offering from Spectro Analytical Instruments. We developed a new method to include the pre-spark signal into the calculation of the total carbon content. This provides evidence as to the quality of the sample. So let's have a look at the extended measuring range and how the new method works. By including the pre-spark time into the integration signal, the correct carbon value can be calculated. So using Spectro's advanced method, the free graphite component is analyzed during the pre-spark time, and the analysis will be corrected. The results this method achieves are comparable with the one from combustion analysis. If the deviation in the carbon content measured is too large, the result is marked to indicate the calculated value will not be accurate, as you see there in the red. This method is not invented to replace combustion, but to take the brunt of sample analysis work, allowing for fewer samples requiring combustion. Control measurements should still be done from time to time. After recognizing the analytical problem, the next step was the identification of the intensity level of carbon in the pre-burn sequence. All the known wavelengths like carbon 165, carbon 193 are too sensitive and show the expected overflow in the detectors. Only the new carbon 148 line was able to cover these extreme intensity levels. The stabilizing ratio calculation is done with a few reference lines like iron 149, which have both lines being very close together and are a perfect fit. Both lines are in the range between 120 and 160 nanometer that has been discovered by Spectro when we changed from vacuum technology to gas fill in the optic. For those who are not familiar with OES, oxygen in the atmosphere is absorbing light, especially UV. To decrease this negative impact, Vacuum was used to open the range between 160 to 230 nanometer for important elements such as carbon, phosphorus, sulfur, and boron. In the late 80s, gas filling was tested. We evacuated the chamber and filled it with nitrogen. Nowadays, we are using argon instead of nitrogen. This reduced again the existing oxygen particles, and we opened up the range all the way down to 120 nanometer. The extended wavelength range down to 120 nanometer in combination with semiconductor sensor technology like CCD or CMOS created new analytical opportunities. Low carbon and nitrogen analysis in the single part per million range are also possible with carbon 133 and nitrogen 149 in the first optical order. Also, small amounts of oxygen 130 at the 130 line and hydrogen at 121 nanometer line can be detected. This is very important for titanium-based alloys. Okay, after a lot of theory, there are some practical results. Sample 1A and 1B are coming from the same heat, but the 1A sample contains approximately 0.2% free graphite, and the 1B sample contains more at about 0.5% free graphite due to different chilling periods. We compared the results to the new advanced method we invented and compare it to combustion analysis. For sample 1A, we can see a difference of carbon of approximately 0.1% between the conventional method with Spark OES and the advanced method. The advanced method is giving the same value as the combustion analyzer. The deviation for sample 1B with higher content of free graphite is even larger. As can be seen, the advanced method is presenting a value very close to the combustion analysis. The picture is similar for the next two examples. The conventional Spark OES is showing a carbon value which is too low, and our advanced method calculates values comparable to combustion. So here and on the next slides, we have the analysis of a certified reference material to show the accuracy of these spectrometers. You can also see the accuracy with the certified reference material on carbon and alloying elements. And with white iron, we have a very precise analysis on carbon as well as all critical elements. It can control the melt. With the gray iron using the advanced Iron 25 program, we have an excellent precision of analysis for the carbon despite the apparent presence of insoluble, otherwise known as free graphite, in these samples. With our advanced method using spectro-belt algorithm, taking advantage of our optical technology, it is possible to determine if there is any free graphite in real live samples. A warning occurs as soon as the sample contains a critical level of graphite. Carbon determination errors induced by graphite are reduced with differences to combustion, typically less than 0.1%. However, the method is not designed to analyze carbon in manufactured components. The analytical result of carbon is correct and reliable. If no result is possible, the operator can directly take action. It is possible to reduce the use of combustion analysis drastically using this equipment only for control purposes. The new method gives a clear indication about the quality of sample preparation. Spectro's carbon and cast iron advanced method can save you money. So, which instrument do we choose? Going back, we have the SpectroTest and SpectroPort, which allow you to bring the spectrometer to the samples instead of vice versa. For a mobile spectrometer, we have excellent detection limits and some possibilities to analyze nitrogen to sort duplex steels even. However, the carbon content in gray precipitated steels may not be sufficiently precise for optimal control of a melt. But there are other applications where just screening where those values are may be pertinent for you. Our workhorse, the SpectroMax, provides for improved detection limits and precision of analysis. Additionally, we have the improved channels to analyze lower levels of nitrogen in samples and, of course, carbon. Precipitated carbon content will be given with total carbon content. Now, the SpectroLab S, our flagship instrument with extremely low detection limits and exceptional precision of analysis due to the CMOS detectors and the ability to do time-resolved spectroscopy. With our optical design, we extend the UV range as well and can analyze gases like oxygen with excellent results. We can measure gray iron for carbon content very well, allowing us to determine both total and precipitated carbon with our special FE25 algorithm. Well, I'd like to thank you very much for your attention while we discuss the analysis of cast iron by optical emission spectrometers, both mobile and stationary. Mobile spectrometers give us an excellent capability for alloying elements, but for best carbon analysis in gray cast iron, we have a special algorithm implementing advanced technology in our stationary instruments to give us total and precipitated carbon analysis, thus reducing your use of combustion and expediting melt control. Thank you again very much for your time. And if you'd like more information, you can find us at our resource library up here, or if you'd like a product demonstration, you can contact us here.
All right, thank you very much, Mike. Everyone who's attending here, this is the time to type in those burning questions that you have. And Mike, I'll let you go ahead and start away once they come in.
Sure thing. Thank you very much, Shannon. One question I got was why can't it be used for quote unquote finished parts or as cast? And this goes for heat treated samples as well. It can't be used for those kinds of samples as cast finished parts because the carbon content is too high, and that is part of the problem. That's why we have such an emphasis on the sample preparation and sampling procedure to get a special sample as opposed to trying to analyze as cast parts. Another question was about ductile iron. This method was actually made for specifically nodular and ductile iron, and it works great for that for the iron 25 by monitoring those additional wavelengths and during the pre-spark time with our special algorithms to get a real total carbon content comparable to combustion. Any more questions? I'm sure some people here would have some questions of interest. I know it was quite technical in certain parts. And of course, you can contact us at these bits of information, the websites up here, as well as for product demonstrations, and also contact us by phone or email here as well. Shannon, I feel like I did too good of a job. Oh, here we go. Can an as-cast part be remelted and quickly cooled for analysis? Now, I'm not a metallurgist such that you're taking a as-cast part and then remelting it, what losses you may have. It is certainly feasible if you find that it is representative of your original melt, then yes, we would be able to use an as-cast remelted and rehomogenized and quickly chilled sample using those copper molds and so forth for the analysis. Yes. So I have had this question for if the technique is possible for handheld, and I would consider that also for portable devices like our SpectroTest and SpectroPort. They do not have the wavelength range, nor do they have the, let's say, power, the background processing power to monitor those wavelengths sufficiently speedy enough to capture that spiky behavior in the pre-spark. It's not just a upwards spike and then drop off. Often what we see are random spikes like in a true inclusion analysis that for those that are familiar with inclusion analysis. So you need a speedy detector in order to capture that. And that is not possible in our mobile spectrometers. So what is the cycle time between iron 25 and iron 20? For a white sample, I would say, well, graphite inclusion free, they're the same basic measurement time, maybe adding a couple more seconds for the iron 25. The iron 25 does extend the pre-spark time if it does detect a significant amount of graphitic inclusion. So that could be up to an additional 10, 20, 30 seconds. And honestly, at that point, it would tell you this sample is not sufficient, is not good enough, if you will, for an OES analysis because there's too much free graphite in there. So it does extend the time somewhat, but it is a great time saver in general compared to having to prep as well as do 100% combustion analysis. And again, this is not a replacement for combustion. This is a supplement. So it reduces the usage, but it's still critical for melt monitoring to have your own, regular schedule for that kind of testing. But it does save you time and consumables. They all came in pretty quickly, and just seeing if there's any more questions.
And if you do think of something later on, please use those contact points there on the slide that you see now to reach out again.
Mm-hmm.
All right. Well, thanks again, Mike, and thanks to everyone else for joining us today.
Thank you, Shannon, and thank you, everybody.
Have a good one.
Thank you.